Hi, what I have here on Workbench today is a ZOYI ZT-XR1 multimeter and battery tester combo. I have reviewed a lot of combo devices on this channel by now. For instance, oscilloscope multimeter combos, multimeter thermal camera combos. I had always wondered what else could possibly be combined with a multimeter and still makes logical sense. Well, here we have it. Zotac just put a battery tester and a multimeter into the single device. So in this video, we'll take a closer look. Zotac sent in this meter for me to review. It is rather inexpensive. Currently it's around $50. As usual, I will leave a few product links in the video description below for those who are interested in getting one after watching this video. The built-in multimeter has 25,000 counts, which looks pretty good. And if we look at the specifications, you can see that the accuracy is also pretty decent, especially for DC voltage measurement range. It's spec'd at 0.05% plus 3 counts. For most of the other voltage measurement ranges you can see here, the accuracy is specified as 0.5%, which is still pretty good. Of course, the resistance and capacitance measurement accuracy is quite a bit lower, but that's pretty normal for these kind of multimeters. So I guess we'll definitely have to take a look at how accurate it is in our testing shortly. Now, as you probably have noticed, this meter does not come with current measurement capability, which could be an issue if that's the only meter you have. But for most of the people watching this channel, this shouldn't be a problem, as you probably already have many multimeters. So the main reason you want to get this one is for added battery testing capability. To the left, we have a dedicated input for the Kelvin clips, and by the way, the clips are also provided. Now, it has this rubberish cover here. Unfortunately, the cover is not attached to the meter, so you could easily lose it. Now, the battery tester inputs should be isolated from the multimeter inputs, as otherwise it could be a huge problem if you are measuring high voltage and then you accidentally touch the battery probe interface. So let's actually verify that. So let's see if any of the pins share the common ground. Excellent, it doesn't seem so. How about the positive side? Very good, at least these two inputs are properly isolated. And if I turn it around, you'll see back here we have a stand. Now, the stand is a little bit flimsy, but it should be adequate for a cheap meter like this. Now, the one thing I actually don't particularly like is the placement of the USB port. It's not very convenient to charge the meter, as to plug in the USB port, you pretty much have to either stand the meter up or put it on the side, which is not very convenient. And speaking of the overall design, it's actually very similar to another Zotac meter that I reviewed a few months ago, and that one is the ZT-XR1. Now you can see that these two are side by side. Judging from the appearance, these two meters look very similar. The ZT-XR1 is a multimeter and thermal imaging camera combo. So the multimeter actually has the current measurement capability. And just like the ZT-XR1, the multimeter is also a 25,000 counts one. So definitely there are a lot of shared designs and components between these two meters, and I would expect the multimeter performance to be quite similar as well. Alright, so let me actually power up the XR1, and of course let's remove the screen protector first. Now the first thing I notice is that we have this split display with graph displayed at the bottom. I think the font ZOYI used on this meter is actually different than the one used on the ZT-XR1. So let me actually power on the ZT-XR1 and let's compare. Yep, you can see the font is indeed different. I actually prefer the font used on the XR1. And of course, on the ZT-XR1, we can turn the graphic mode on and off via this button here. You can see that. But on the XR1, I think we're stuck with the graphic display, and there's no way to turn it off. Personally, I don't like that, just because it is really not that useful in most of the cases, and I'd rather have larger font size for the displays. Anyway, so definitely the firmware has been tweaked between these two models. Alright, I just stood up the meter so we can actually see the screen better. Let's plug in the leads and do some measurements. The supplied leads feel pretty cheap, but that's pretty much what to be expected for a cheap meter like this. Let me plug in the leads. Let me actually remove the shroud. You should keep them on if you are doing high voltage measurements, but for our testing, I don't need these. I just want to see the tips. You can see these tips are not gold-plated. I wasn't expecting anyway. For voltage measurements, we actually have 4 modes. Let me cycle through. Here is a DC voltage mode, and here is AC voltage mode. Here is DC millivolt range, and here we have AC millivolt range. And we go back to DC. By the way, the beeper sounds a little bit scratchy. So let's actually take a look at the millivolt range first. It actually has 2 ranges in millivolts, 25 millivolts and 250 millivolts. Of course, it auto ranges between the two. In the lowest 25 millivolts range, which is one we're in currently, we have a resolution of 1 microvolt. Of course, just because it displays down to 1 microvolt doesn't mean it actually can measure it. So let me start with 1 microvolt on the voltage standard, and let's get a feel of the sensitivity of this meter in the millivolt range. Alright, so now let me dial in 1 microvolt. And that's 1 microvolt. And I don't think I see anything on the screen here. It's still jumping around. 2, 3. Yeah, you can see that we're registering something, but it's not definitive. 4, 5. I think it is registering something, but it's definitely jumping around. 6, 7, 8, 9, 10. So you can see from the graph here, we sort of have that resolution of 1 microvolt, but from the display here, it's jumping all over the place. So definitely you need to take the accuracy with a grain of salt. Now let me dial it up. Now let's do 10 microvolts at a time. 10, 20, 30, 40, 50. Yeah, there's definitely some offset. 60, 70, 80, 90, and 0.1 millivolt. In the grand scheme of things, I suppose down to this range, it is still pretty good. But there is a constant offset here. So let's do 1 millivolt at a time. 1, 2, 3, 4. Yeah, you can see that when we're dialing in millivolts, you can see the accuracy is actually pretty good. 5, 6, 7, 8, 9, 10. Okay, let's do 10 at a time. 10, 20, 30. Now we lost a digit because of this switch to the higher range. 40, 50, 60, 70, 80, 90, and 100. All right, now let's take a look at the volt range, and we'll do 1 volt at a time. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. No problem. Anyway, now let's actually take a look at the AC measurement range. For AC measurement, we also have 2 ranges. One is for millivolts, the other one is for volts. And I'm going to skip the millivolt range. Let's go directly to volts. And I'm going to turn on the variac. For comparison, I'm using the BM788BT. Okay, let me ramp up the voltage. The update rate is specified at 3 times per second, which is similar to most of the budget meters and definitely is adequate. So let me keep increasing. And you can see that the readings are actually pretty consistent between the 2 meters, which is good. Let me ramp up to the max. And you can see that, no issues. And one thing I like about this display is it actually displays the frequency as a secondary, which is very convenient. Now let's take a look at the resistance measurement mode. And first thing, I'm going to short out the leads. you can see that the auto ranging is definitely on the slower side. Of course, you can always do manual ranging, but we'll keep it as auto ranging. And let's see what the residual is. Now, because these are not gold plated, you can see that the residual value is jumping all over the place. And if I press it harder, it's lower. So let's actually route it out first. The first resistor we're going to measure is this 100 ohm 0.1% tolerance precision resistor. And let's take a look. And that's a problem of these non-gold plated probes. You have to really try to scrape in. Yeah, now you can see we're actually getting almost exact 100 ohm. But if I just casually touch the leads, you can see the reading is all over the place. All right, let me remove the rail. The next resistor we're going to measure is this 1.25K 1% tolerance resistor. So let's take a look. And no issues. All right, the next one is a 10K resistor. No problem. And last, let's try a 1 megohm resistor. And you can see, although the auto ranging is not the fastest, it's actually quite adequate. And let's see the next range. And this is continuity. Let's take a look. And this is where the coating of the leads also come into play. Because these are not gold plated, probably is a little bit oily. You can see that it doesn't really make reliable contact. But if I try to put the tips together, and you can hear that actually it is registering correctly. The reaction is also pretty quick, but we don't see that registered on the screen here. Yeah, the sound definitely reacts immediately, but let's see how long it takes. It took roughly half a second for the screen to register, and also the beeper just sounds quite a bit scratchy. And here is our diode mode. Let's see if we can detect a PN junction here. And you can see there is no beep, but we're able to measure the forward voltage drop of a PN junction. Let's try a white LED. Yeah, we're able to light up the white LED too. Now let's take a look at the capacitance measurement. The first capacitor I'm going to measure is this 10 picofarads capacitor. Let's see if we can register that. Of course, that's going to be tricky because of the leads, capacitance, and whatnot. But let's actually see if we have the resolution for a 10 picofarads capacitor. So you can see we did register a jump between 30 picofarads and 40 picofarads. So we actually were able to measure that 10 picofarads. Of course, I can always route it out, but because we have these long leads, the capacitance actually is all over the place. But relatively speaking, we are able to measure that 10 picofarads. Very good. So now let's take a look at another one. This one is roughly a 100 nanofarads capacitor. I think the actual value is a little bit off. Let's take a look. Yep, close enough. And how about this one? That's a 1 microfarad capacitor. Yep, no issues. I'm going to jump directly to one of the larger capacitors, and this one is a 15,000 microfarads one. Let's see if we can measure that. And it's taking quite a bit of time, which is normal. At the end of the day, we are able to measure 13.9, and that is close enough. So this reading is quite comparable from what I got from other meters. And the next mode is temperature. And of course, we have a thermocouple that is supplied. Let's actually plug that in. And does it work? Let's see here. Yeah, it works with no problem. Of course, as I mentioned earlier, one of the reasons you want to have this meter is for its battery internal resistance measuring capability. So let's actually take a look at that. And here are the supplied Kelvin clips. You can see that the build quality is actually quite decent. Now, the one complaint I have is the connector is actually proprietary. This one looks actually pretty similar to the one from HR10, but they are not exactly the same. In fact, these are not interchangeable at all. Anyway, let me plug it in. And to switch to battery tester, all we need to do is long press the SPAT and DMM button. Battery testers typically use AC conductance measurements, so the output waveform should be an AC signal. Let's take a look on the scope. And I'm going to acquire the signal. And wow, that doesn't look like a sinusoidal at all. That's very interesting. So you can see we're measuring roughly 2 volts peak to peak, and the voltage is fine, but the waveform I would expect to be a sinusoidal, but it's not. Let me see if we change the measurement speed, whether or not it changes the waveform. So let's do slow, nope, medium, fast. I guess it doesn't really impact the waveform. And currently you can see that the frequency is at around 1 kHz, which is also pretty standard. But I don't know why the waveform is not sinusoidal. As a battery resistance tester, it should be able to measure resistance. So let's actually first measure a precision resistor, the same resistor we used before. It's a 100 ohm, 0.1%. So actually let's take a look. And it's measuring 103 ohms. That's definitely not correct. Let's actually see if we have any residual readings. The residual reading should be 0, but it's showing as 0.3 milliohms. Of course, this is actually not really the error that we saw earlier, but nevertheless, it should be 0 because these are 4-wire Kelvin sensing. And let's see if the rel works here. Okay, it does work. So let's rel it out and let's take another look. So no, you can see the measured result is actually quite a bit off. And as a comparison, you can see using the Finersi HRM-10, we are able to measure exact 100 ohm. So there's definitely some accuracy issue with the measurement. And by the way, the reason it's showing red color is because we're actually having this interval here. You can see the low interval is 3 volts, the high interval is 4.5 volts. This is meant for you to bin your lithium-ion batteries. Anyway, we'll take a look at that later. But right now, let's actually try to measure something else. In theory, we should be able to measure capacitor's ESR as well. Now, one of the key benefits of using a battery tester to measure the capacitor's ESR is that the capacitors can be charged. Since the meter is capable of measuring voltages up to 100 volts, whether or not the capacitor is charged, it doesn't really matter to the meter. But for a standard LCR meter, a charged capacitor with significant DC bias can damage the meter. Anyway, let's take a look at the ESR reading of this 15,000 microfarads capacitor. Here we're reading 15 milliohms, and I don't know if I trust that reading, but let's verify that with a different meter. So okay, so at least it's agreeing with the Finersi HRM-10. So here is the reading on this ZT-XR1 measuring a lithium iron phosphate battery. And you can see the resistance is measured at roughly 14 milliohms. So let's actually try measure the same battery with my Finersi HRM-10. You can see that the results are slightly different. Now let me try to measure the internal resistance of this lithium-ion battery. Now, of course, to make good contact, it's going to be very difficult, and I'll try to space it out a little bit so that at least we'll attempt to use the 4-wire sensing here. And you can see that when it beeped, it tells you that you get a stable reading and it's at around 30.4 milliohms. So let's remember that number. And of course, the number turned white. That's because it's actually within the interval we set between the low and high. Anyway, so let's take a look with the inertia here. I'm going to do the same thing. Try to spread it out. Yeah, you can see, actually you can't because of the glare. Now you can see the reading is actually quite comparable. All right, time for us to open it up. All right, now I open it up, and the general layout looks fine, but I don't quite like these two electrolytic capacitors here. You can see that they're not glued down, so they would vibrate, and over time, they potentially would add strain to the soldering joint and would fail. Anyway, that's something I wanted to point out. And here is a reservoir for the Kelvin clip. And here is our USB port. And as I mentioned earlier, I don't quite like this USB port at the back of the unit because it's just very inconvenient. And also another problem is that it actually adds significant strain to the board, and it depends on how they secure it. Actually, let's take a look at that. So I think it's fine because it's actually going through this shroud here. So anyway, there is a possibility you could potentially yank it out of the board if you're not careful. The microcontroller used on this board is an Artery 30F series ARM Cortex MCU. And here we have a DC to DC converter. And here, by the way, is our isolation chip. That is I believe, a Pi 122EU31. And you can see this optocoupler here as well. So this actually provides the isolation between the two parts of the circuitry. And this part is actually the digital multimeter, and this part is the microprocessor. From our testing earlier, the battery internal resistance testing portion is also isolated from the digital multimeter portion. And here is our digital multimeter chip, which is a DM1109CEN, and it uses an external voltage reference. The reference used here is an ICL8069. And throughout the board, you can see we have quite a few of these RCS8552 op-amps. And just like most of the cheap multimeters, the input protection is quite inadequate. You can see we only have this tiny PTC, and we, by the look of it, have two of these transistors forming an input voltage clamp, and that's about it. And we don't have any MOSFETs for input transient suppression. At the end of the day, I suppose it's an okay multimeter, and as I mentioned earlier, the battery internal resistance testing has some accuracy issues. But for the price you pay, I suppose that's what you get. I hope you enjoyed the video. If you liked it, please remember to give it a big thumbs up, and don't forget to subscribe to the channel for more videos like this in the future. Your participation makes videos like this possible. Thanks for watching, and I will see you next time.